Hi everyone. So today I have for you a INMO problem and it's actually a number theory problem which is pretty nice. So let's get started. So the question is, find all natural numbers MPN where P is prime greater than or equal to 5 such that this equation is satisfied. Okay. Now look at this question. So whenever you see a power of P, right, one thing to note is that if you take a power of a prime, all its divisors are actually powers of prime. So that allows you to factorize powers of prime pretty nicely. So whenever you see a power of a prime, a good thing to try, and especially when you see some kind of a polynomial expression on the left, one nice thing to try is factorization. So indeed, in this case, you can factorize. If you bring this minus 3 to this side, you can factorize it. So let me write down the factorization for you. The first observation is to solve this is to factorize after you bring 3 to this side. Okay, so that is, you will see that it is 4m plus 1 into m square plus 3 is equal to 3 into p power n. Okay, so now you have 3 into p power n written as product of two numbers. Now notice that is not exactly a power of a prime. Unfortunately, there's a 3 outside, so it's 3 into a power of a prime. And this p cannot be 3 because it's been given that the prime is bigger than or equal to 5. Alright, so what are the different possibilities? Okay, in what different ways can you factorize? Well, from the fundamental theorem of arithmetic, that there's a unique prime factorization, you know that this 3 into p power n can be split and put into parts here. You know, the number of ways of dividing this into two parts, there are very few. So let's start. Can it happen, let's wonder whether we can eliminate the simple cases. Can it happen that is 1 into 3 power n or 3 into p power n and so on. So 1 into 3 p power n, can these things happen? It's easy to eliminate that. Notice that because m and n are natural numbers. And if m and n are natural numbers, forget n for a minute, since m is a natural number, m is bigger than 1, so 4m plus 1 is bigger than 5. Okay, notice that 4m plus 1 is bigger than or equal to 5 because m is at least 1, and m square plus 3 is bigger than or equal to 4 because m is at least 1. So this is at least 5 and this is at least 4. So there's no chance that these numbers can be 1. So you cannot have a prime factorization. I mean, you can't have a factorization here is one of them is 1 and the other is 3 into p power n. You can't even have 3 into p power n. You see, one of the factorization that could happen is one of them is 3, the other is p power n. That also can't happen because no number can be 3 here because both are, bigger than 3. So which means that no matter how you try to factorize this, a piece of p sits in both of them. So in other words, 4m plus 1 and m square plus 3 should share a common factor. And that common factor must be some power of prime. Now, in number theory, is there a way to compute common factors? Indeed, the greatest common divisor or the highest common factor, whatever it's called, can be computed via the following famous Bezout kind of an identity. So notice that if I could get some linear relation between the two, I can actually compute the GCD. In fact, there is a nice linear relation. So let me write it out for you. So if D is the GCD, so this is a typical thing in number theory. So if D is the GCD of 4m minus 1 and m square plus 3, then D will divide the product. D will divide the product here. So D will divide this difference. So D will divide 49. Okay. So if the GCD of 4m plus 1, sorry, and m square plus 3 is D, then clearly D divides 49. D divides 49, which means the greatest common divisor is a factor of 49, but the only possible factors of 49 are 1, 7 and 7 square, right? 1, 7 and 49. So D can be 1, 7 or 49. These are the only possibilities. Okay. Now, can 4m plus 1 and m square plus 3 have a GCD of 1? No, we already argued that they should share a common factor. The common factor, therefore, it can share can only be 7 or 49, which means that the prime p that is common has to be 7. Okay, so we discovered that p must equal 7. That's a good progress, right? We already found p has to be 7. There is no other way. All right. So once you get p is 7, the second thing to note is that the common factor can only be a power of 7. In fact, that power of 7 can only be 7 power 1 or 7 square. So there are two cases. Okay. So case 1 is when the common divisor between 4m and m square plus 3 is 7. Okay, now if the common divisor between these two is 7, then notice that at least one of them cannot have a power, in the prime factorization of these numbers, you cannot have more than 2 sevens, okay, here, for both of them. That cannot happen. At least one of them should have only 1 7. Which means that at least one of them is either 7 or 3 into 7. Okay, so the cases are 4m plus 1 could be 7, or 4m plus 1 could be 3 into 7. Okay, so when I write this x looking symbol, I mean into. Okay, or it can happen that m square plus 3 is 7, or m square plus 3 is 3 into 7. Okay, so these are 4 possibilities. Now, if you quickly do a calculation, 4m plus 1 is 7, m plus 4m is 6, which is not possible. There is no natural number. And if you look at 4m is equal to 21, though, there is 4m is equal to 20, m is 5, but if m is 5, if you plug in m square plus 3, m is 5 here, you see this 28, and 28 has a factor of 2, which is not there on the right hand side. So this also is not possible. Now you look at m square plus 3 is 7, you'll see m square is 4, if m square is 4, m is 2, but if m is 2, okay, if m is 2, when you plug in 2 here, you get 4 into 2, 8 plus 1, 9, and 9 has 2 factors of 3, right? But there's only one factor on the right, so that's not possible. Finally, m square plus 3 is 21, which if you rearrange means m square is 18, but 18 is not a perfect square. So there are no solutions in the case when, the GCD of m4m plus 1 and m square plus 3 is 7. The only other case that is remaining is case 2. And that is when 4m plus 1, m square plus 3, GCD is 49. Okay? So this is the only other case that is left. So now what does that mean? What does it mean to say that the GCD is 49, which means both of them have a factor of 49 in them, and that is the greatest common factor. So if the greatest common divisor of 4m plus 1 and m square plus 3 is 49, then what does that mean? It means that at least one of them can have only the maximum power of 7 that can divide it must be 49. Okay, so which means again by the same logic, either 4m plus 1 in this product, 4m plus 1 is 49, or 4m plus 1 is equal to 3 into 49. Also, it could be that m square plus 3 is 49, or m square plus 3 is 3 into 49. Okay, so these are the different possibilities. Alright, so now let's see which of these are possible. So if 4m plus 1 is 49, then you can rearrange and you'll see that m must be 16. Okay? Now if m is 16, you will see that this will be 16 square plus 3. It's a quick calculation to do. 16 square plus 3 is 259. Okay, it's 259. And if you do a calculation, you'll see it's 7 into 37, which means that this number has a factor of 37. Okay, this number has a factor of 37. So 4m plus 1, if it is 4m plus 1 is 49, then m square plus 3 has a factor of 37, but then there is no factor of 37 on the right. Okay, so this is 1+. If 4m plus 1 is 147, then 4m is 146, but 146 is not divisible by 4. So again, there is no solution here. Okay. Alright, what about m square plus 3 is 49? If m square plus 3 is 49, then you see that m square is 46, but there is no perfect square, which is 46. So again, there's no solution. So the only last thing that is possible is m square plus 3 is 3 into 49, which is m square plus 3 is 147, which means m square is 144. Wow, so this has a solution. So m square is 144. Okay, m square is 144, so which means m is 2. And you see this indeed works. Okay, so if you put m is 12, so we can actually summarize here. So m is equal to 12. If you put, you will see that when you put m is equal to 12, this is basically 144, and this is 49. Okay, so 49 has 2 factors of 7, and here 147 again has a factor of 49. So you'll see that there are 4 factors of 7, so n is 4. Okay, so you can check n is 4, and p is, of course, we already know is 7. So this is the only solution. So this particular Diophantine equation has only one solution, m12, n4, and p7. And there you have your INMO. Bye.